Okay, today I will continue with the time reversal property of the Fourier transform. By definition, the Fourier transform is given by this integral formulation. And the objective here is to find the Fourier transform of f of minus t. So we replace the argument by minus t instead of t. And we will note f minus of omega, the Fourier transform of f of minus t. So using the definition of the Fourier transform, we get f minus of omega, which is the Fourier transform of f of minus t, is by definition given by this expression. Let tau be equal to minus t. This means that d tau is equal to minus dt. Then we will replace minus t here by tau, and the limits of the integral will change because the tau is equal to minus t. So we see here plus infinity minus infinity. F tau exponential j omega tau. So j omega tau can be replaced by minus j of minus omega tau. So the minus which is here will reverse the limits from plus infinity to minus and minus to plus. And what we are seeing here is by definition the Fourier transform of ft evaluated at minus omega. Time transformation, it means we may have situation where we have time delay, and also we have some compression or dilatation of the function ft. So the transformation here is a composite transformation that results from time shifting and time scaling at the same time. So f of at minus t0, we can write it as f of a factor of t minus t0 over a. So clearly here that we see a delay of quantity equal to t0 over a. And we have a time scaling with a factor a. So if we will proceed first by time scaling of this function, so we will use this relationship that we have already proved in our previous slides, that the delay in time results in multiplication by an exponential function in the frequency domain. So here, instead of having t0, we have t0 over a. It means we are expecting to have f of omega exponential minus j omega t0 over a, because the delay here is seen as t0 over a. Now, if we use the time scaling property, so we will rescale the function by omega over a, and we will multiply the Fourier transform by the factor 1 over the absolute value of a. And this is what we are seeing here. So this is the results of time scaling, and the exponential is due to this delay in time. So this is a composite transformation that results from two different transformations that are the time shifting and the time scaling. The duality is one of the important properties of the Fourier transform. And we start always with the Fourier transform pair. Ft gives f of omega by the Fourier transform, and f of omega by the inverse Fourier transform gives ft. So the Fourier transform is given by this relation, and the inverse Fourier transform return back to our signal in time, and it is function of the Fourier transform of ft. we will prove that if now we will reverse, instead of having f of omega, we will replace omega by time, as you are seeing here. So what it should be now, the Fourier transform of capital F of t, function of f lowercase. It means the original signal in time. So it is 2 pi f of minus omega when we assume that ft has a Fourier transform equal to f of omega. Starting from the definition of the Fourier transform and the inverse Fourier transform, this implies that if we replace minus t in this expression, so we'll put here minus of time. Now we will replace omega by s in this integral expression. So we will have the following results. Now, by replacing the time by omega, so I will replace the time by omega, I will get these final results. It means f of minus omega equal to 1 over 2 pi time the red expression. Or the red expression is 2 pi multiplied by f of minus omega. We remark that this red integral, it is exactly the Fourier transform of ft. And this is what, this is the claim that we have imposed. F of t Fourier transform 2 pi times f of omega. And this will end the proof. An example, if we take, for example, a constant a, we know that a delta t, a times the Dirac function, its Fourier transform is equal to a, which is constant. So here we are in time, and here we are in the frequency domain. How about if we will reverse having a constant a? It means in time. What it should be now, it's a Fourier transform. It's like I have ft gives a capital F of omega, and then I will reverse f of capital F. What it should be, it's a Fourier transform. So the 2 pi f of minus omega, it is a delta of minus omega, but the delta of minus omega, it is equal to delta of omega. And this gives these interesting results. So any constant has a Fourier transform equal to 2 pi a, the Dirac function in the frequency domain. The differentiation property, we see it in studying linear time invariant systems described by differential equations, where we need to solve these differential equations. We move to the frequency domain by applying the Fourier transform. And then when we get the solution, we return back to the time domain by applying the inverse Fourier transform. So always we are starting from the definition of the Fourier transform and its inverse Fourier transform. If I will differentiate now this expression with respect to time, so df over dt, so I will enter the differentiation operator inside, and I will integrate. So now I have a function dependent on time. It will be j of omega exponential j of omega t multiplied by f of omega, which is this expression. So here we see that j of omega times of f of omega, it is what? It is the Fourier transform of df over dt, because this is by definition the inverse Fourier transform of j omega times f of omega. If we continue the differentiation with respect to time from this side, so starting from this expression, if we continue the differentiation, n equal to 1, 2, 3, 4, nth derivative of f with respect to time, we will see at each differentiation, we are multiplying j of omega by j of omega. So the nth order, the nth derivative of f with respect to time will be j omega power n f of omega exponential j omega t d omega. And this is seen as what? As the inverse Fourier transform of this function. So as a result, we can say that dnf dtn, its Fourier transform is g omega n f of omega, or this function in the frequency domain has an inverse Fourier transform equal to the nth derivative of f with respect to time. Pay attention, when we would like to get f of omega from the Fourier transform of df over dt, so if we note g of omega as the Fourier transform of the first derivative of f with respect to time, so we can recover f of omega by dividing by j of omega. But we have to add a constant times delta of omega, because many function in time, if we will differentiate them, we will get the same function in time. So when we would like to return back to f, so we have to add a constant times delta of omega. And here is clear that if I will multiply both sides by j of omega, I will have j of omega delta of omega, and this is existing only at omega equal to 0, which gives j omega f of omega equal to g of omega. We will see a lot of examples in the next videos showing that we may have k different from 0, for example, in the case of the step function, and other functions that are not differentiable at omega equal to 0. Now, if we start from the definition of the Fourier transform and the inverse Fourier transform, we have the Fourier transform of df over dt. It is always equal to j omega f of omega. Now, we would like to show some fact. If we calculate the direct Fourier transform of the derivative of f with respect to time, so this is exactly g of omega. Now, using integration by part, if I will define u to be exponential minus j omega t and dv equal to df, this implies that v equal to f and du will be minus j omega exponential minus j omega t dt. Applying the integration by part rule, so we will get this part plus j of omega, the Fourier transform of ft. Okay. Now, this value is equal to 0, but this value divided by j of omega is not always equal to 0 when we take the limits at plus infinity and minus infinity. So now, if I would like to recover the Fourier transform of ft, noted f of omega, so I have g of omega divided by j of omega minus these limits, which is split into two terms, limit at plus infinity and limit at minus infinity. So in the general case, these limits are not equal to 0. So we may have situations where these limits are not equal to 0. One example, as I said before, is the step function. So this is a common error that student may fall in. For example, if you take ft to be the step function of terminal value equal to 1, and you note f of omega to be the Fourier transform of ft. Now, if I will differentiate ft with respect to time, I will get delta. Delta of t is the Dirac, and its Fourier transform is equal to 1. Now, if I will apply the differentiation property of the Fourier transform, I will put j omega f of omega equal to 1, which leads to f of omega equal to 1 over j of omega, which is absolutely wrong. So I have to add plus k delta of omega. And we can explain it from these results. We are here saying that the limit at infinity is 0 because the step function is 0 at minus infinity. But at plus infinity, the step is equal to 1. And this expression, this limit, is not equal to 0. And this gives exactly the pi delta of omega. So we will prove the Fourier transform of the step in the next slides. So before I do that, I would like to make connections between the frequency differentiation and the time differentiation properties of the Fourier transform. So we start first from the usual definition of the Fourier transform, and our final objective is to prove that if I will multiply a function ft in time by a polynomial function minus jt power n, so this is a complex that could be real or complex depending on n. So this will result on a differentiation of the spectrum with respect to omega. The proof of this result is too easy. So now if I will start from the definition of the Fourier transform, if I will differentiate f of omega with respect to omega, so I will enter the differentiation operator inside the integral, which gives minus gt ft exponential minus j omega t dt. And this, by definition, it is the Fourier transform of minus gt ft. It means minus gt ft has a Fourier transform equal to df over d of omega. And this is the result that we will retain, that minus gt times ft equal to df over d omega. Obviously, if we multiply the same function by minus gt, we are expecting to differentiate this term with respect to omega one time more, which gives the second derivative of the Fourier transform with respect to omega. If we continue multiplication in time by minus jt, so we will have minus jt power n, so there is a bracket which is missing, minus jt power n ft, we'll have a Fourier transform equal to the differential n by d omega n of f of omega. So now we will try to get the Fourier transform of the step function in terms of the sine function. Why we are doing this? Because the sine function has an average equal to 0 at time equal to 0. So the sine t is minus 1 when time is negative, equal to plus 1 when the time is positive. So the step function, which is 0 for time negative, 1 for time positive, can be expressed in terms of the sine function by 1/2, 1 plus sine of t. If we will differentiate the sine function with respect to time, we will have 0 here, 0 here, but at time t equal to 0, we have a step. We have delta, we have a Dirac function, so the sine t is not differentiable at time t equal to 0. So we will have a Dirac function with the amplitude here 2 times, because we are switching from minus 1 to plus 1. What you are seeing here is just the amplitude and phase of f of omega. So the Fourier transform of the sine function, we can get it from the differentiation property of the Fourier transform. It means j omega f of omega, where f of omega is the Fourier transform of ut, is equal to 2, which means that f of omega equal to 2 over j of omega. And here the plus k times delta of omega is equal to 0, because the average value of the sine at 0 is equal to 0. So the k will be equal to 0 in this case. So now the step function is ut is equal to 1/2 plus 1/2 sine of t. It means f of omega will be equal to the Fourier transform of this quantity. So here we have a constant, and we know that a constant has, by the duality expression, the Fourier transform of 1/2 is pi delta of omega. And the 1/2 sine of t has a Fourier transform equal to 1 over j of omega, and this leads to the famous result of the Fourier transform of the step function, which is 1 over j omega plus pi delta of omega. How about now the time integration property? So since now we know what is the Fourier transform of the step function, so we will use these results to prove the integration property of the Fourier transform. So now, assuming that ft has a Fourier transform equal to capital F of omega, so now gt is the integral of minus infinity to t f of tau d tau. Okay? And the Fourier transform evaluated at omega equal to 0. So we will have exponential at 0 gives 1. So we will have integral minus infinity to plus infinity ft dt. So here we are using our famous identity related to the convolution of ft with a step function. And we know that a convolution of any function ft with the step functions results on the integration of the function ft from minus infinity to t. So I will invite the student to go back to the previous slides that I put in Blackboard and also to my solved problem to return back to this basic definition of the convolution of any function with the step function. So now, since ft star ut, ft convolution with ut, it is an integral of the function f from minus infinity to t. And this is what we are interested in. We would like to get the Fourier transform of this function in time. So it is a convolution product. It means it will be the Fourier transform of f star u. And we know that the Fourier transform of the convolution is the product of the Fourier transform of ft times the Fourier transform of ut. And this is what we are seeing here. So convolution in time results on multiplication of the two spectrums in the frequency domain. So ft gives f of omega, and ut gives the Fourier transform between brackets. So now if I will multiply f of omega pi delta of omega, delta of omega is existing only at time t equal to 0, at omega equal to 0. So we will have f of 0 delta of omega times pi, and we will have a factor 1 over j f of omega. So we see when we will integrate, we divide the spectrum by j of omega. When we will differentiate, we have j omega multiplied by f of omega. And we have an additive term okay, which is a constant time, the Dirac function at omega equal to 0.